Okay, so what we were doing in the last class, we were looking at multigrid methods, right. We were looking at series of mechanisms by which we could accelerate convergence of our schemes, numerical schemes. So these are in a sense modifications to a fundamental scheme. You have a fundamental scheme and now you are asking the question, is there a way by which I can make this scheme faster, meaning from the point that I start the computation to the time that it takes, wall clock time. I look at the clock and say it takes so much, the time that it takes for me to get the solution. Okay, I want to reduce that. Am I making sense? I am not really interested in other details. I mean, there are situations where you can look at, right, you can say that the whole is equal to the sum of the parts. If I minimize, if I optimize the individual parts, then the whole will also get shrink down. But you will see sometimes that does not quite work out. When you try to shrink one, the other expands and so on. So we have to keep our eye on the fact that the metric, the measure that we are using to see whether we have made an improvement is we start and we look at the clock, it stops and we look at the clock and we say yes, it is taken less time. Okay, never lose sight of that, because it is easy to get caught up in all the numbers, CPU times, all of this kinds of stuff, and lose sight of the fact that the overall time is not either reducing, so you are putting in effort but you are not getting anything out of it. Fine. In the last class we looked at a particular scheme, right, the last sort of half of that class we looked at a particular scheme which was essentially multi-grid methods, and the idea was that we are going to use multiple grids, just to recollect, multiple grids in order to accelerate convergence. Fine. And that, where did that come from? That came from the fact that we said that high frequencies, when we say a signal, see now today I will use a little signal processing kind of terminology. When we say high frequency, right, when we say high frequency, we have already noted from a previous demo that when we say high frequency, we mean high frequency with reference to a grid. High and low are comparative term, they are terms that you use to compare two things. So you need two things and you have to have an other, right. So the other is the grid, the underlying grid. What is the structure of your underlying grid? So on an equally spaced grid, a high frequency and low frequency with reference to that grid are defined. And there were schemes that we saw where high frequencies decayed faster than low frequencies. See, now I am careful, there were schemes that we have seen where high frequencies decay faster than low frequencies. That means that there are schemes for which that may not necessarily be true, right, in which case we need to do something for that. Today I will tell you something about that. Okay. Then so what we basically said was, well, if the high frequencies decay faster than low frequencies, and then we have this low frequency error with which we are trying to contend, essentially the grid that we have at hand is struggling to decrease that error, why not transfer the problem to a coarser grid, so that this low frequency error on the fine grid appears to be a high frequency error on the coarse grid. Okay, and therefore will decay faster on that coarse grid. That is the idea, that is the basic idea of multi-grid method. Okay. Now today what we will try to do is we will try to write out the whole scheme. So first I will recollect where we left it, then we will try to write out the whole scheme, and then we will see what are the steps that we need to take in order to, how should I say, make sure that everything is fine. There is a little patchwork that we need to do, right. There are schemes which may not be inherently high frequencies decaying faster than low frequency, we may have to do something for that, that is one thing. We still want to transfer the problem from a fine grid to a coarse grid, but we may have to do something for that. Okay, that is one thing that we have to do. And the other thing is, all I have said so far is it is going to run faster, it is going to decay faster. Will it? What is the effort involved in doing this? How much work are we actually doing, right? So before you write the program and look at the wall clock time and so on, we are going to ask ourselves the question, how much work is it actually going to take in order to do this? Okay, work in the sense of computational work. There is also implementation related work, and I will sort of say some things about that as we go along. Is that fine? Okay. So first, just to recollect where we were, we started off, remember that the grid size we talked about was H. So this is a typical grid size. What that means is that if I have, that is supposed to be equally spaced, it does not quite look equally spaced. If I have equally spaced grids, right, a typical grid size is H. And if I have a linear problem, and I will tell you what to do when you have a non-linear or quasi-linear problem, linear problem. I chose Laplace equation to I chose Laplace equation as an example, but it could be any system of equations that we are talking about. AH PH equals FH. We are trying to solve this, and what I had indicated was that we iterate this a few times, or if it is a time marching scheme, we march in time, right, a few time steps. So we do this, what was the symbol that I used for the number of iterations? Was it alpha?
N times N.
N times. N times. I am going to regret that, but anyway, N times. We are going to iterate it N times. Okay. So then what do we do from here? Remember the algorithm, we get the residue, so we get RH, which equals FH minus pH, where this phi is that intermediate solution, capital phi is the intermediate solution. We get the RH, then what? We transfer RH to F2H, right. If you want to write it as a an equation, in books that you may look at, they may write something like F2H. This is typical notation, right. So if you can actually write a matrix form of this. I will recollect for you what each of these things, right, we will go through that. So you transfer from RH to F2H on the grid whose size is 2H, you then solve either solve or you iterate a few times or take time steps or appropriately, okay, and do this. If this was N1 times, this could be N2 times. They could be the same, they could be different. If you have some magical reason for making them different, it is up to you, okay. Then we said, look, right, if you start with a very fine grid, it is possible that the 2H grid is also reasonably fine. So you can then compute after iterating a few times, and then you say, oh, it is not converging fast enough, I am not happy with this. You can actually compute a residue there, which you transfer to F4H. Am I making sense? Okay, and then consequently we will solve and repeat this process. At this point, actually, you know, the phi is not actually phi, it is a correction. The phi is, if you think back to the algorithm, phi was actually a correction. So how does the reverse mechanism work? You take the phi 4H that you have got from your iterations, that is your iterate. You could go on, but I will tell you what happens from phi 4H, and you transfer that to E2H, that is the correction at, okay, and the new phi 2H equals the old phi 2H okay. Now you have lots of options. See, this is the thing about the algorithm, developing the algorithm, you can see there are lots of options. If you want, and I would do this, you can also sort of iterate a few times there, m times if you want, okay. So you iterate at that level and then you get a phi at that level, right. The f does not change if you want, right. Then you can transfer okay. This transfer, by the way, you could write, if you wanted to write it as an equality, just so that if you look at books, I want you to make sure that you have the notation. You would write this as E2H equals along the same lines I4H to 2H Phi4H, right, and you can actually write it as a, if these are vectors, you can actually cook up, you can find out what this matrix is depending on what kind of interpolation or whatever it is that you are doing, right. We will look at, I will give you the appropriate terminology, we will go over this blackboard again one more time, right. Is that fine everyone? And then you would say Phi H equals right, that is the correction at the H level. Maybe m times, and at the finest grid you always ask the question, you compute RH, say I am repeating now, I am repeating the first line now, we are back to the first line, but you can ask the question, have we converged, right, you always iterate on the finest grid a few times and ask the question, have we converged? Does that make sense? You want, I mean the reason why we are making this effort is I want a grid on that, I want a solution on that fine grid, because that is the resolution that I want, that is what I am looking for, right. I have decided, I have looked at the problem, I have looked at, I have an idea, I have a sense as to what the flow features are like, and I have said okay, I need a grid that is 1 millimeter in size, let us take actual physical dimension, I need a grid that is 1 millimeter in size, I want a solution on a grid that is 1 millimeter in size. So having decided that, I pick an H which is 1 millimeter and I go through this process, right. So I want to make sure that when I finally decide yes I have the solution, I am making the decision on the 1 millimeter grid, not at the other grids, okay. The question always arises at this point, okay, I do not care about the other residues that we have calculated. Is that fine? Is that okay? Are there any questions? Now we will go over this with a little detail, we will check out, fine, we will just check out a little of the few of the things. How do we decide, what is the point here, how many times do we iterate? Is there a mechanism by which we can decide how many times to iterate? Is that just an arbitrary parameter? Should we have a method by which we should decide how often to iterate? Think back to our demo. See, I said there is a highest frequency that we can represent on a given grid, okay. So if I am going to go from a grid, okay, maybe we should say something about grids first, okay. So if I am going to go from this grid to a really coarse grid, it has only one unknown, right, I am going to go with 3 interior points to 1 interior point, then I have to make sure that I have iterated enough on this that there is no component of what I am going to transfer, the residue that I am going to transfer, which has a frequency higher than what this can represent, okay. If you go back, think back to the demo, otherwise what will happen is you will get what the signal processing friends in electrical engineering call aliasing. Basically that high frequency error will fold back into the low frequency end, am I making sense, and we will start getting a residue here which is spurious, which is not the right residue, okay. So if you talk to your friends who have done signal processing in electrical engineering and so on, they would call this process either decimation or downsampling. So if you are going to do decimation or downsampling, the first thing that you have to do is you have to remove the frequency content that you can't represent on the coarse grid. If you can't represent it, it will only show up as an error, it will only contaminate the residue that you have in the coarse grid, okay. So one possibility is you iterate enough number of times so that all that high frequency error, that is right now that is what we have, all that high frequency error is eliminated, one possibility, okay. We clearly have to come up with some other way to do this, because remember I said there may be schemes that do not decay high frequencies, there may be schemes that do not decay high frequencies fast enough, right, there are all sorts of issues. So but we have to decide, so you iterate enough number of times, you have to make sure that you have done it enough number of times that you have only the frequency content in the residue that you are going to represent on the coarse grid. Is that fine? Otherwise anything that you transfer from the fine grid to coarse grid will show up in the wrong place, okay, right, okay, it will show up in the wrong place in our frequency domain, that is if you look at it in terms of frequency, okay, right. So that is bad, that is not good, that is not what we want, fine. The second thing is, so this we have to see, is there something else that we can do here, right. What else do we have? You transfer from here, maybe we'll stick with this, maybe I'll finish with this first and then let me see where can I write that. I have this, I am already at RH, I'll write it here. So just say you have a scheme, so before I get back to that, let's just say, right, we'll take an aside and look at this, let's just say you have a scheme that's not dissipating fast enough, or right, or you decide that you're going to iterate a fixed number of times or take time steps a fixed number of times, 5 time steps, 10 time steps, right, simply because you remember something I told you earlier when we were doing SOR. I basically said, look, don't wait for it to converge to a certain extent because you don't know how long it's going to take. You are committing unknown amount of CPU time, right, unknown number of iterations, always bound the amount of computation that you're willing to do. So you say 5 times, I'm willing to iterate 5 times, but that might not eliminate all the high frequencies, but we know one operation that eliminates high frequency. We have seen it when we did our looking at high frequency, when we first encountered high frequencies decays faster than low frequencies. That's what, that's either the heat operator or the Laplace operator. We have seen it, that's guaranteed, that really kills it, right. So if you have in 2 dimensions, if you have 4 grid points, you take the middle fellow and take the average as the average of the 4, right. We have seen that it's a solution to Laplace's equation, right, that sort of decays and it decays quite fast. I don't want, I mean I actually have a value here, right, so I don't want to just throw away what I have at that point. So instead what I will do is I will take the average of these 2, average of these 4, right, that gives me a central value. I already have a central value, I will take the average of those 2. What do I mean by that? I have values A, B, C, D, and at the center I have E, okay. This is what we would call Laplacian smoothing. What I would do is I would say A plus, right, that is the Laplace operator, we recognize that for an even grid. Okay, that is like taking omega equals half in SOR, right, omega equals, does that work out half? Omega equals what? 1.5? 0.5? I am not sure. 0.5, okay. I just throw that, I am just throwing that out there to see, okay, fine, I am just painting you, it's okay. So what do we have? So this of course turns out, so the way this would work out if you were to, so you can see the Laplace operator here. The way this would work out if you are going to actually apply it to R. So what are we going to apply it to? We are going to apply it to R. I have iterated a few times, I have decided say 5 times, I have iterated this equation 5 times, I have had enough doing iterations at that level, I compute the residual, I have no clue what is the spectrum, I have no clue what frequencies RH has. All I want to do is I want to eliminate those high frequencies, okay. So what I am going to do is, I know this will do it, I know the Laplace operator will do it for me. So I am proposing to smooth R before I do the transfer. Am I making sense? I am proposing to smooth R, this is called Laplacian smoothing. So you would write R at any grid point as is that okay? If you work out that fraction that I had earlier, you will see it will be 4 times, so the R smoothed would be basically that, okay. So you can do one sweep, you do not feel comfortable, do 2 sweeps, I guarantee those high frequencies will be gone. Now transfer the smoothed R, okay. So now we are going to add a new, we will add a new step, now we have a new improved step that we have, so which is why I strategically left myself a gap here, right, okay. So smooth RH, fine, and then do a transfer, is that fine. So at each level you can do that, at each level you can smooth RH and then do a transfer. So this F2H now, this F2H is not going to have any content that it cannot, right, that grid can't represent, and then as a consequence you can iterate this, and again I would iterate it a few times. Smooth again, so we will have smooth and do the transfer, okay, fine. So at every point when you are doing a transfer, you smooth, you calculate, compute the residue, find R, that is how it goes, that is how it works, okay. Is that fine, everyone? Okay. So this is as far as making sure that there is no contamination, there is no contamination when going from the fine grid to coarse grid, okay. So we need to do one more thing, we will look at, is that fine, okay, everyone, you can do smoothing, of course you can do a similar kind of smoothing on the way back, that is we will get to that. The next thing that we do is we want to look at this, what is this operation, what is this operation that we have, okay. So how are we going to do this average, I mean how are we going to do this transfer RH to F2H, how do we do the actual transfer? I think I can remove this, if I need it I will come back. Right, okay, but in order to see the transfer we are going to actually look at what kind of grids, what are these multiple grids that we are going to generate. We look at how it works, there is an underlying structure, we look at that, okay, and then look at what is the transferring, what is this business of transferring, what are the ways by which you can transfer. So we will start at the coarsest level because that seems to be and see if we can get a pattern, that seems to be the easiest. So the coarsest level is one grid point, interior grid point, 3 grid points on the whole. The next level is five grid points, is that right? What is the next finer level? Nine. Where do you think this is going? So it is going to be basically going as 2 power n plus 1. Now you know why I did not want n iterations there. Anyway, 2 power, I have also used m, k plus 1. Okay, is that fine? Right, 2 power k plus 1, so k equals 1, k equals 2, k equals 3 and so on, fine, okay. So you could for instance if you wanted a fine grid, so you won't start with, I won't start with 1001 by 1001, right, because that is thinking decimal. I would start with 1025, I would start with 1025 grids. If I had a 2-dimensional problem it would be a 1025 by 1025 grids. As I said, start with 1025 grids and the next level of grids would be 513, you understand, and 257. Now you understand why you need to go to multiple levels. This is 257 grids, this is still pretty fine. It is just that we want the answer on, if 1 meter length, we want the answer on something that is of the order of 1 millimeter. Okay, 1025 is close enough. okay. So then you would go to 129 and so on, and you can go all the way down to 3, right, if you want. So this is the number of levels that you can transfer. So if this is H, it is 2H, 4H, 8H, fine. We have tried, I mean I think we have gone up to like 7 levels or something of that sort, right, okay. So you look at this process. So now we know we can pick up grids like this. This is on 1D. What about 2D? You can take the Cartesian product of it obviously, right. So that could be 3 by 3 grid. Am I making sense? To that you can add, maybe I will use a different colored chalk. Oops. That is a 5 by 5 grid. Am I making sense? And we can go on, you can make it a 7 by 7 grid and so on, right. You can make it a 7 by 7 grid, maybe I will choose that. Is that okay? Get a 7 by 7, right, 9 by 9 grid, okay, I am back 9 by 9 grid, sorry, thank you, 9 by 9 grid, doing suddenly 2n minus 1 instead of 2n plus 1, 9 by 9 grid, that is one way to do it, right. So I am constructing it up. The other thing is, if you had a 9 by 9 grid, you can throw things away in what we call the checkerboard pattern or the chessboard pattern, okay. So you do not have to, you can for instance you can start, you can retain this grid point, retain that grid point, retain that grid point, retain that grid point, okay. Then you can retain this one, retain this one, retain this one. Am I making sense? Oops. Am I making sense? Right, it is like the black and white squares of a chessboard. Is that okay? So there are obviously, once you go to 3 dimensions, 2 dimensions, there are different ways. So this is called coarsening. There are different ways of doing coarsening. Okay, is that fine? So now what we want is, so we want, if we want to go from a coarse grid, if you want to go from a fine grid to a coarse grid, in the multigrid, right, I said signal processing, they would call, say you go through a downsampling or whatever, the multigrid terminology, that is called a restriction, you restrict, right, you restrict. So what you would basically do is, you would now, this is what I was talking about, how do I find that, I will write that here. So what are the ways by which we can do it? Right. So one thing is just pure simple injection as they call it. What you do is you just throw away the points that you do not want, right. So if you have, okay, let us look at this. So you have 5 grids and you want to go to 3 grids, you just throw this away, that is one way to do it, right. Another way to do it, of course, a better way to do it, another way to do it, a little more expensive, we have looked at it in the last class, you take the average, okay, and a familiar average. The average would be, if this is p minus 1, p plus 1, the average would be, so we are going from where this is residue, remember. So rp minus 1 plus 2rp plus rp plus 1 divided by 4 would give you the value at that point. Looks very suspiciously like Laplacian smoothing, right, very suspiciously like Laplacian smoothing, okay. These are all at h, this will be rp at 2h. The value here would be twice this plus each of those divided by 4. Okay. What if you are doing in 2D? How would you do it in 2D? I am not going to do 3D because it is I mean you can work it out, but it is a pain to draw the picture, but I will do it in 2D. Okay. So this would be a full, the best transfer and the most expensive transfer, most operations. You want to get that, you want to transfer the value at that point. So you have 1, 2, 3, 4, 5, 6, 7, 8. 8 of those, so what are we going to do now? 8 of those plus 8 of these, right, divided by 16. Am I making sense? 1, 2, 3, 4, 5, 6, 7, 8, add up all of those plus 8 times the central fellow divided by 16. Am I making sense? So the logic is now you can see the where it is coming from. So that would be a of course I mean you could in theory add more points to it, right, you could increase the support, so to speak, you could add more points to it, but this is in itself there is a certain expense, but you are taking all the points that you are planning to throw away. You are taking data from all the points that you are planning to throw away, that is the idea here, right. You are going to, if you are going to take this point, its neighbors are not going to be used, right. So in this case if you are going to take this point, if you are, unless you are doing the checkerboard pattern, unless you are doing this pattern, if you are just doing the standard, right, the standard coarsening, this is called the standard coarsening. So if you are going to do only the standard coarsening, then you are going to throw away all the neighboring points, right. So this should be determined really by all the neighboring points. Am I making sense? So you would say summation what should I say? So L in the surrounding set, L not equal to P simultaneously, or LP not equal to, I should write that a little more carefully, LM, so except for that one plus 8 times okay, is that fine? So this is how we do the transfer, this is how we are going to do the transfer. So this will allow you, if you work it out for a grid, I would suggest that you start off with a one dimensional grid. You are never really going, this is only for the sake of our explaining the algorithm to ourselves. You are not going to really write this matrix as such, but you can, just for the fun of it, to see what the structure looks like, try to write it out and see what it looks like. Okay, so you do the transfer, okay, you do the transfer this way. Am I making sense? Is that fine? Right, you do the transfer, there are different ways by which you can do it. You can do the averaging depending on 1D, 2D or 3D, right, and you transfer it to the coarser grid. Maybe we will come back to this, I leave that portion. What else do we have? So we are now going through this whole process. How do we get back? How do we do this transfer? How does the reverse transfer take place? So I want to go from a coarse grid to a fine grid. So I have to interpolate. So now see there will be cases. So you have to look at the various cases. One case is the point is actually in this set. Okay. So typically the notation that you would write is this is the grid, well this is the grid at 2h and that is the grid at h and 2h, but it is okay. What you would basically, so if this belongs to the finer grid, just transfer the data directly. If it does not belong from the coarse grid, there is no candidate, take the average. 1D it is obvious. You go to 2D. In 2 dimensions, if this grid belongs to the fine grid, transfer it directly. If it does not belong, but it happens to be, so in this case this is a funny mesh. Let me draw another mesh. Where can I draw it? I will draw it here. I need to erase something. I will erase this, I no longer need this. There we go, okay. So what you have done is, this is the coarse grid. That is the coarse grid, okay. I am doing standard coarsening, that is the coarse grid. So if it belongs to the same grid line, if it is on the same grid line but does not belong to that mesh, take the average, same thing, okay. So you can take, in order to find this, you can take the average of these two. If it does not belong to the same grid line, so this works even here, right, even in the vertical direction it works. If it does not belong to the same grid, that is like this, a little more complicated. Then you take the average of the 4, okay. Is that fine, right? So on this side take the average this way, on that side take the average that way, and in the center one take the average of the 4. Have I missed anything? I think that covers all possibilities. Is that okay? That covers all possibilities, right? So that is how you transfer from a coarse grid back to a fine grid. So the correction, that is how the correction would be transferred from a coarse grid back to a fine grid. Is that okay? So if you say that I want phi 2h to go to EH, this is what you would use, fine. So now we come to the critical question. So we have got an algorithm. What we are able to do is, we have the solution, presumably you iterate a few times on the fine grid, right, and we can transfer down residues to coarser and coarser grids, transfer back corrections to finer and finer grids, and we have these nuances, residual smoothing and so on, do all of those kinds of things, right, all that neat stuff. We have an algorithm. What does it cost us? Okay, what is the cost? On what grid do we want the solution? So back here, on what grid do we want the solution? We will pick a big problem, 1025. So maybe I said 1025 by 1025 or 1025 grids, 1025. Okay, this is the grid on which we want the solution, fine. So if you were to take either whatever equation you are solving, Laplace's equation for example is a good place, and you are iterating, it would take a certain number of iterations to get a solution on the grid of size 1025, a solution that is to your satisfaction, right, 5000 iterations. 5000 iterations, 1025 grid points. Am I making sense? Okay. So if you were to in between transfer the problem to a 513 grid point grid, a mesh that has 513 points, then 2 iterations here is the same as 1 iteration there, right. Remember when we are talking about one of the things that I said, when you find out how fast is my computer program running, what did I ask you to do? I told you to find CPU time per grid point per iteration or per time step, okay, CPU time per grid point or per iteration or per time step, that gives you a measure of your program, what it is up to. So if you, right, I don't, why should averaging be more expensive just because I am on a coarser grid? That does not make sense, right. So I don't expect, right, unless you do something really bad in your programming, I don't expect that the 513 by 513 CPU time per grid point per iteration will be more than this. So the work per grid point is the same. Okay, the work per grid point is the same. So now I want to get a measure, right? So I will say, wait a minute, if you didn't do multi-grid, you would be doing so much work on 1025 grids. So I will call one sweep or one time step or whatever scheme that you are using through this 1025, your finest grid. I will call that one work unit, right. We will start off by defining what do I mean by this work. So we will call that one work unit. Am I making sense? Sweeping through this your finest grid, making one iteration or one time step, I will call that one work unit. So if I have one work unit here, two iterations here will correspond to one work unit, or basically one iteration here would be 1/2 work unit, one iteration here would be 1/4 work unit, right, and so on, 1/8 work unit. Am I making sense? So it is better for me to be doing 8 iterations here in comparison to one iteration there. Okay. So I will show this process of going from coarse grid to fine grid in a graphical fashion, and this is a standard graphical fashion that people use in order to demonstrate multi-grid method, and because the picture evokes an image, I mean there is a letter, it gives it a name. So what you do is, this is at the level h, I go from h to 2h, 2h to 4h, 4h to 8h, we will go 4 levels, back to 4h, back to 2h, back to h. Okay, so this represents one cycle. Because of the way it looks, it is called a V cycle. And of course, you know it is called a V cycle because there is going to be another cycle, right, a different cycle. What is a different cycle? I basically look at this and say, wait a minute, you mean this takes one work unit and this takes only 1/8 work unit? I want to spend a lot of time here. After all, I am always going to end there, right? So I want to spend more time here. So what you do is you go h, 2h, 4h, 8h, 4h, now you have a choice, then go back to 8h, 4h, say yeah I like that, I like that, right, fine. This is called a W cycle. And obviously W cycles come in lots of flavors, right. The minute you create the innovation, lots of things that you could go 8h, 4h, 2h, come down, or you could go 8h, 4h, 2h, 4h, 2h, 4h, 8h, you can see I want to spend a lot of time down here, right, because it doesn't cost me anything, right, as long as I come back and I iterate a few times at h, because then I say hey, residue has gone to 0 at h, I have got the solution. Am I making sense, right? Okay, are there any questions? The work units in one dimension go as 1, 1/2, 1/4, 1/8. How about in 2D? It goes down faster, right. So in 2D, so in one dimension, this is work units per sweep or time step or iteration or whatever, 1 by two power k kind of a thing, okay, it's like 1 by 2D. That is great. Now we know 3D is where we want to do this, though I have not shown anything. 3D, so the savings are enormous. 1D you may not, you do a toy problem just to learn how to do this, but you have to do at least 2D, right. in order to say that wow, I have got something really great. So this is going to be 1 and that is going to be 8, right? Am I making sense? 32, what is that going to be? $128, 64, 2 power, this is 2 power 2, 2 power 4, 2 power 6, 64. So this is going to give me 2 power 8, 256. The powers of 2 are worth no 3k, fight one, but you have to pick the right power of 2. They are not only worth knowing, but you have to make sure you pick the right power of 2. No use knowing the powers of 2 if you pick the wrong power of 2. Okay, fine. Fine. I mean, just look at this. You just go down, right? You just go down a few levels. This is nothing. I mean, so you take 10 time steps on this, 512 time steps on that, right? And that's like taking 1 time step on the finest grid, or 1 iteration on the finest grid. Why would you not want to hang around there, right? So if you are doing in 3D, if you are doing 1025 by 1025 by 1025, that's a lot of effort. 1 billion, more than a billion, right? But you come down here, it's not that bad. It's really not that bad. Okay, as long as you make sure that you're always checking for your convergence at the, don't forget that. Okay, there's one last thing, there's always a little wrinkle that we can throw in. Say, why start at a fine grid, right? This was, remember when we talked about initialization, we said, hey, one way to do it is start at the coarse grid and transfer. Yes, we can do it here, right? So why start at a, so you basically say, why should it start there? Start here, right? Start at 8H, transfer it to 4H. That's the way to do it. You understand what I am saying? You already have it. You already have it. So the critical thing is, what is the, so this multigrid methods, okay, lot of people just don't get into multigrid. You don't see multigrid methods used as often as they should be. Okay, this is my observation. There are a lot of research being done, lot of enthusiasts. If you want to go out on the net, you can search for, you can just search for MGNet. Enormous amount of resources, huge amount of resources, right? The critical thing that you have to do to make sure that all of this works is something that you have to do anyway. So you have to make sure first that you implement this, right? If you do this, you are set. What are the things that we have here that are different from your standard solution? Say standard solution is given a grid, take time steps, right? Given a grid, take time steps or do iterations. So first of all, your program that you have, has to be somehow changed, right? So if you are talking about Laplace equation, if you have phi and you have a Laplace equation solver, right, that you are using right now, you just have a solver, right, that says, oh, give me the boundary conditions whatever in some fashion and solves Laplace's equation, right. What you need to do is you need to convert that into a function that can be called. So you convert it to a function get phi, which takes the grid, or the grid level or whatever it is, which takes the grid level. Am I making sense, right? Possibly an initial guess and all of that kinds of stuff. I don't put everything else. Takes a grid, right, and it should return to you. It should return for you the residue. Should do one iteration, come back and return a residue, or do n iterations and come back and return a residue. Am I making sense? So your program that you have right now that solves Laplace's equation or whatever it is, it has to be changed. It has to become a function because you are now planning to put something piggyback on top of it to make it run faster, right? So you are going to say, do this on a 1025 by 1025 grid, and it should come back one iteration and give you a residue. Or you should be able to say, take 10 iterations. This is a little better. Take 10 iterations with this initial guess, okay. So maybe I will make it a little more. With this initial guess, at the level k, take 10 iterations. I am just making it up, take 10 iterations, okay. So now you have got this, you can just pass it, right, and it takes 10 iterations, and what it returns is the residue. You can then do, you need to have, what is the next thing that you need to have? You have to be able to do Laplacian smoothing to it, you have to smoothen it, right. So you have to have some smooth which takes a residue, right, and returns a smooth residue. Am I making sense? Right, as to whether you actually implement it in this fashion, whether you actually have these functions, you will have to figure it out. But what I am saying is these are operations, they are atomic operations, you implement each one of these, test them, make sure that they work. If you got this, then the rest of it is relatively easy. Then what is the other critical thing that you need? Transferring. You understand what I am saying? So you have to have something I H2 or 2 if you want, whichever, I do not know what you call it, you know, capital H. Let's otherwise we will have too many 2 H's, okay, right. Fine grid, coarse grid. Or it takes R and gives back F, whichever way you want to do it. So this gives me R, this gives me R, this also gives me, this gives me an F, okay. In fact, if this is a generic function, it will take 2 arguments, it will take the k, because you need to know, not k, it will take the k, right, you need to know what level you are. The actual implementation, as I said, the actual implementation will vary, so you will need to know what level you are, you get the f, then what else do you need? You need the other way around, fine to coarse, you need correction equals which will take you from fine to coarse to back to fine. Am I making sense? If you do this, this is the critical part, if you do this you are set, right, but the idea is to implement this, make sure that for a grid, any grid it works. Do not worry about whether you are solving Euler equations, Navier-Stokes equations, Laplace equation, it does not matter. The minute you start worrying about water, then that gets to be a problem, okay, is that fine, okay, right. So I guess that's what we have for multigrid methods. You can get a tremendous amount of speed up, we will see where it goes, okay, just try it out, see where it goes.